Making deeper neural nets. Yeah, let's do it. Let's make some basic neural nets and then just like stack it deep until that's up. We'll take a look at how to fix that, and then we'll make a crazy deep neural net. We're going to use MNIST as our experimentation. And we're just going to use fully connected layers, just simple neural nets, like you see there on the right. Without the colors, though, there's just going to be no colors. I want to do this because going deep is a secret to great success. That's where AlexNet started off in 2012. That totally changed image recognition with neural nets. And it started with 8 layers, and then 8 layers the next year. VGG went to 19 layers, then 22 layers, then ResNet just went to town with 152 layers. And you know, before this, people were having a really hard time getting their networks to do more than just a few layers because of vanishing gradient and exploding gradient problem. Let's do it. All right, I'm just using Colab here. Let's do it. Let's see how deep we can make our network using rectified linear unit. All right, so that failed at 32 layers. Yeah, so we can see here with 4 layers, it was able to get up to good accuracy pretty fast. At 8 layers, at 16 layers, struggled, had to do 2, and then here at 32 layers, we ran out of budget. Okay, so, some of you are probably asking me, why would you use stochastic gradient descent? Okay, well, we could use something more impressive like Atom. So maybe with Atom, we could pick up where we left off before. Well, that didn't work out well. It failed to train. With just stochastic gradient descent, it was able to do that. So all this extra fancy optimization doesn't necessarily get us to train deeper layers. I'm not saying that Atom isn't good. It's good. But if we want to go deep, we may have to try something else. So we've got a couple other options here. So we've got these other options here. We've got sigmoid, right? It tries to push it between 0 and 1, tanh. Well, I'm just going to skip right to tanh. Let's give that a try. So let's just copy this using an activation of tanh, and we're going to start. All right, we made it to 64. It was somewhere between 64 and 128. So tanh with stochastic gradient descent seems to be doing pretty good. Let's 104 layers. We haven't done anything particularly, innovative here. We're just using tanh and the initializer that we just start with. This initializer, it's a pretty darn good initializer. Let's just take a look, at these guys here, and they didn't really have great initializers way back then, and initialization was pretty tricky. So this default initializer used to be called Xavier. This is the more general version of it. So that's really helped a lot. That's why now with just default configurations and using a nicely behaved activation function, nicely behaved initializer, we can go to really deep number of layers and still actually train. This didn't quite train, but hey, we got to 94 layers. Okay, well, what could we do now? Let's try adding batch size. Let's try changing the batch size. So by default, it's using 32. Let's copy this, go here, say batch size. Let's do 100. Let's see if that makes a difference. I'm going to start at 94, and here we go. Made it to 114 layers using 10H and batch size of 100. Okay, well, I think it's probably time to try something a little bit more clever. How much deeper can we go than 114 layers without using anything really sophisticated? We're just using good initializers, good activation function. I mean, this is just the default that comes with the Keras layers in TensorFlow now. What did these guys do? Well, they did things like skip connections and ResNet. Well, it did ResNet. What's happening in ResNet? Well, I have this layer here, and it outputs some signal. And if blue wants to see that signal from red, orange has to replicate that signal and send it to blue. That means that if there's some important information, really important information here that red needs to share with the blue, then orange has to spend its weights replicating, basically reinventing the identity function and sending it to blue. What if the signal from red passed to blue and orange could just annotate it, add to it, modify it a bit? Well, that's ResNet. It's taking the signal, sends it to blue, and orange gets the signal also and adds its signal to blue. So that's ResNet in a nutshell. And there's no reason why you need to just do it one layer at a time. Actually, in ResNet, they have like 2 intermediary layers. But you could add like 20 or 30. Okay, let's go back here. Let's code in a ResNet layer and see how deep we can make this go. Four hundred layers. That's pretty crazy deep.